really work through some stuff here and get to our solutions a lot faster. Okay, so what we're going to start with is the idea of what we've already seen. Here's just a basic little circuit with a resistor. We've in the past been calling these voltages, like this is a 9-volt battery, and this is the positive terminal and this is the negative terminal. But we're going to start calling this the EMF, the electromotive force, and it's just some potential that we need to start driving the positive charges forward. Okay, and over here we've got some resistor R, nothing crazy there. Now, when we think about this circuit system, and we've talked about this previously, if we were to measure the voltage across the resistor, so we put a little voltmeter in here, we know on this side of the circuit here, we're at 9 volts at every point throughout that. But when we go across this resistor, the negative terminal is sitting here at 0 volts, which means that all of this over here is also at 0 volts. And if that's the case, then the voltage across the resistor better be 9 volts, because that's the voltage difference that we're measuring. The difference between 9 and 0 is 9. Okay, so that means this one resistor, oops, that was unprecedented. That means this one resistor here is using 9 volts worth of potential. Okay, now we have written this previously as Ohm's law. V equals IR. The voltage, 9 volts, equals some current times some resistance. And if we have the resistance, if we say, oh, let's make the resistance 4.5 ohms, then we could say 9 volts equals I times 4.5 ohms. And then dividing each side by the 4.5, we would find that the I is equal to 2 amps, 2 amps worth of current. Okay, that's just Ohm's law. But we can rewrite Ohm's law in a way that makes a little bit more sense for a Kirchhoff law. If we rewrite Ohm's law, I'm going to rewrite it that the voltage minus the current times resistance equals 0. And what I'm really saying here is that voltages minus voltages equals 0. Or what I'm saying is that when you go around a closed loop in a circuit, when you go from here all the way around and you come back to where you started, your voltage hasn't changed. If you were at this point right here and you end at the same point, that 9 volts, you haven't had a change in voltage yet. And that's what this is saying right here. When you go around a closed loop, you have not changed your voltage. Your voltage difference is 0. You start and end at the exact same position. So that's a Kirchhoff loop there, or a Kirchhoff law right there. As you go around a closed loop, your change in voltage equals 0. And what we can see then is that voltages that we might gain, such as through a battery, minus is the voltage that we lose, such as going across resistors, have to equal 0. Okay? We'll talk about conventions on how to look at that momentarily. The second Kirchhoff law we have is, let's make a slightly more complicated circuit. So here's a circuit with a parallel branch. Let's just throw a resistor in here and throw a resistor in here. So we'll call this R2, we'll call this R1. Here's our EMF to the side. Well, we know that initially, in what we've seen with some of the problems we've done, is that we're going to have a current going from positive to negative. So we're going to have a current coming out this way. We'll call this I1. Well, once we hit this node right here, this junction, to split into the parallel branches, we're actually going to get 2 currents to occur. We're going to get a current coming down this branch here, we'll call this I2, and then we're going to have a current coming down this branch here, I3. And what we know is that when these I2 and I3s come back together, we're going to get coming out here I1 again. okay? And I3 runs all the way to here until it hits that node, okay? What this means is that I1 has to equal the sum or the addition of I2 plus I3. We split I1 into two pieces. It was coming down and then it split and then it came back together to reach I1, or the total voltage here. We could rewrite this if we wanted to. So this is what's known as a junction law. What happened up there? Did you see that? This is a junction law. But basically, whatever we have coming in has to equal what we have going out. Okay? So your ins have to equal what you're coming out for your currents. So in this case, when we look at the node right here, I1 is coming in, it equals what's coming out, I2 and I3. We can also set this as ins equal positive value and outs equal negative values, and we could rewrite this as I1, it's going in so it's positive, minus I2, it's going out because it's negative, minus I3 equals 0. And these two look the exact same. We've just used a little bit of algebra to move them around. What we see here is that we have to conserve this current. We can't lose it anywhere. Whatever we have initially, we have to have in the end. So that current has to be a constant value. So those are our two laws that we're going to have here. We're going to have this law, the change in voltages equals 0, going around a closed loop. And then our junction law is just stating that our currents, our ins and outs, have to equal each other, okay? And we're really going to write it like this down here. That's going to be the way that we're going to write it in class. There's going to be an interesting way why we do that and how we set that up, okay? So let's take a look at an example problem for a Kirchhoff loop and just show what it is we're looking at and some of the conventions that we're going to maintain while looking at them, okay? So for a little example here, this is a rather, it's not a large circuit, but it's bigger. So we're going to have an EMF here, and we're going to go up, have a little bloop bloop, a little bloop bloop. Here's another EMF, a little resistor, comes back up, and then we go this way, we have a resistor, and then we've got another EMF, and then here's another resistor, and then down to here. Okay, yay, we did it. Okay. We are going to say that our EMFs are as follows. This is 3 volts. This is 6 volts. This is 6 volts. And then we're going to say our resistors are going to be 2 ohm, 2 ohm, 2 ohm, 2 ohm, and then 4 ohm. Okay? So the question is, what are the values of the currents running through all of the branches of this circuit? Okay? Because we're going to have a current running on this side, either this way or this way. We're going to have a current through the middle, going either up or down. And we're going to have a current on the right side, either going around or around. And while we don't know what the values of any of these currents are, I guess an even bigger question is, what directions are the currents even going? And how would we even begin to approach that? So what we're going to do is this. Since we don't know what direction the currents are going, or even what their values are, we are just going to create a direction of the current and just assume that we're correct. Okay, we're just going to say the current is going in this direction and we are right. I mean, we could be wrong, that's totally fine, but we're going to see at the end of this that if we are wrong, it will be readily apparent and there's an easy switch of just a negative sign and then you're correct. Okay, so let's just pick directions of currents here. Now, the one thing we need to be careful about when picking directions of currents is obeying our junction rule. So let's just do this for our currents. Let's just say this here we'll make I1. We'll just say this is I2, and we'll say this is I3. Well, if we were to write this out, that junction rule would be I1 plus I2 plus I3 equals 0. And that's a no-no, because what we just said is that 3 positive numbers equals 0. That can't happen. For our junction rule to be true, we can't have everything going in, because now we have nothing going out. It's like we tried to funnel a bunch of water into one junction of a pipe, and then none of the water came out anywhere else. It just magically disappeared. So that can't happen. We need at least one of these terms to be going the opposite direction. Let's just make it, well, let's make it I2 and I3. Oh, let's just make it I2. Let's just make it I2. Okay? So what this will change here in this junction equation is we'll now have I1 minus I2 plus I3 equals 0. And the ins equal the outs. Okay, so this is allowed to be doing, this is a fine junction equation now. Okay? Now, so this is first equation. That's a good one. Okay. Likewise, if we can't have everything coming in, we also can't have everything going out, because then everything will just be negative, and where are you getting the current from? Now what we have to do is that we've established directions of currents, and we just completely chose randomly those values. It doesn't matter if those values are right or wrong. All that matters is that you chose them, and some are going in and some are going out. We don't know the true answer yet, but that's totally fine. Okay. What we're going to do now is we're going to choose a direction of the loop. Okay, and this is where the Kirchhoff loop comes into play. This is the magic of it. What we're going to do is we're going to walk around the circuit in closed loops, so we know the net voltage, or rather the change in voltage, will become 0. And these loops can be kind of chosen just at random, with one little caveat here. If I say I'm going to start here in my loop, and I'm going to go all the way around the circuit and come back to where I started, that is a closed loop. That's a Kirchhoff loop. We can use that. At the same time, I can say, hey, I'm going to take this other side and I'm going to go around a direction. Now, it doesn't matter what direction you pick. It does not matter at all. We're going to go around the same direction just so that we can kind of show you what's going on here and what could happen in some scenarios, okay? But it doesn't matter what direction your loop is going. Just choose a loop, okay? Choose a loop. It doesn't matter. So just like choosing the direction of your current didn't matter, choosing the direction of your loop does not matter. You just have to choose one, okay? So just put them there and you're totally fine. What we're going to do from here is we're just going to walk the loop, okay? So when you're walking through a loop, anytime you go with the current across a resistor, so when you go with the current across a resistor, you are going to get a minus IR, okay? Because you're losing voltage. Okay, you're losing that potential, so you're going to get a minus IR there. Just like we showed up here, whenever we walk across this, we have a minus IR whenever we're going across this simple circuit. Okay, so let's literally just walk around this system. I'm going to start here at the top, and as I'm walking, I'm going across this 2 ohm resistor with the current I1. So I'm just going to have minus I1 times the resistor, 2 ohms. And then we're going to keep walking. Walk, 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 walk. I hit my junction, and now I'm turning down. When I turn down, I'm still going with the current I2, and I'm going across a 4 ohm resistor. So it's going to be minus I2 times 4 ohms. Okay? Now as I walk, 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 I'm going backwards across a battery, across an EMF source. Okay? When you're going backwards across a battery, you're actually losing that voltage. you're going from 6 to 0. And the difference between them, final minus initial, is 0 minus 6. So we're losing across this battery here 6 volts. So minus 6 volts. We continue to walk. We hit this junction and we make a left. Walk, 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 walk. We are back into the region of I1. The current I1 is going that way because it's looping all the way up and then all the way around because we just chose it to do that. So we're going to get another minus I1 times 2 ohms. And then as we walk, 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 we have to go back over this last EMF right here. And since we're going from 0 to 3 volts, final minus initial, 3 minus 0, we're actually going to gain a voltage. So whenever you go through a battery in the proper direction, you're gaining that EMF, you're gaining 3 volts. And since we've arrived back to where we started, that's going to equal 0. So we literally just chose a current at random, directions of them, chose a direction of our loop at random, and then we just walked around obeying these 2 laws. Whenever you go with a current across a resistor, you're losing the voltage. When you're going from negative to positive on a battery, you're gaining the voltage. And when you go from positive to negative on the battery backwards through it, you are losing it. Okay? So we can clean this equation up a little bit. And we'll come back and do that momentarily, but that's a good equation right there. Okay? Take a minute here, just pause this video, and I'd like you to walk through this loop on the right-hand side by yourself. I'd like you to just try to write that out, see what you get for the loop. Let's just start the loop right here, and then remember, we're going that way, okay? So try to set up this Kirchhoff loop for that right-hand side of the circuit, and we'll see what we get. Bum, bum, bum. Bum, 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 bum. Okay, you paused it in theory. So let's see what we got here. When we start off here, we're going backwards over the 6 volts. So the first thing we're going to get is minus 6 volt across that EMF. And then now we're going across a resistor. But this I3, that's the domain we're in right now. This is I3 going up and up and up and then around. We're going against the current across that resistor. And since we're going against the current across that resistor, we're actually going to gain that voltage. So we're going to plus I3 times 2 ohms, okay? Because remember, when you go with the current across the resistor, you're losing. So when you oppose the current, you better be gaining there. So we've gone across this, we've gone across that, we walk around, we turn up. We're going with the direction of the battery, so we're going to gain 6 volts. And then now, as we continue to walk, we're going against the direction of I2 across the 4 ohm resistor. So that's going to be plus I2 times 4 ohms. And then we come up, 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 up. We make a right. We're going against the current I3. So we're going to add again, plus I3 times 2 ohms. And I believe that takes us back to the beginning, and since we've arrived back to the beginning, this has to equal 0. And that is a good Kirchhoff loop equation. Okay, so our 3 equations we have here are I1 minus I2 plus I3 equals 0. Minus I1 times 2 minus I2 times 4 minus 6 minus I1 times 2 plus 3 equals 0. And then the last one we just wrote, minus 6 plus I3 times 2 plus 6 plus I2 times 4 plus I3 times 2 equals 0. Okay? We have 3 equations now, and we have 3 unknown variables we're solving for. I1, I2, and I3. And in mathematics, for every unknown that you have, if you have an equation, if you have as many equations as unknowns, you should be able to solve for all of the unknowns there. Whether you're using a substitution method or dividing equations, we're going to use a little bit of linear algebra here in something known as a row-reduced echelon form, but you can also use lower upper triangular solvers, LU factorization, You can rearrange matrices using Gauss-Jordan pivot structures. Like, you can do all sorts of things here with math. That's not my job to teach you that. You'll see that in your linear algebra courses later in life. But we have 3 equations and 3 unknowns, and that means this is solvable just based off of what we've written. Okay? So what we're going to do here is we are going to set up what is known, and this is a cool way for get your calculator to do some work for you. We're going to set up row reduced echelon form. And in your calculators, this is known as RREF. Okay, so we'll have to find that in a second to show you what that is, but that's what we're going to be setting up here. Okay, now the way we set up row reduced echelon form is we need to rewrite these equations real quick, and we're going to rewrite them in a specific way so that every single equation has I1s plus I2s plus I3s equals the EMF. Okay, so every equation is going to set up I1s plus I2s plus I3s equals EMF. Okay, so they're all going to have I1 plus I2 plus I3s equals EMF values. So if we look at equation 1 real quick, well, that's already set up nicely for us. That equation is just I1 minus I2 plus I3 equals 0 EMF. Okay. If we look at the second equation we have here, well, let's combine our I1s. We've got minus 2I1 minus 2I1, so that's going to be minus 4I1. Technically, there's an ohms there. I'm going to ignore it because all of these are in terms of volts. So I'm just going to ignore the ohms units for a little bit because we're kind of in the math mode right now, just trying to crunch numbers. Okay. For I2s, I've got a minus 4 I2. So minus 4 I2. And then how many I3s do we have? Well, we don't have any I3s, so we'll put plus 0 I3s because 0 times anything is 0 equals. And then on the left side of this equation here, I had minus 6 volts plus 3. So that would give me, in theory, minus 3 volts. But I need to put that to the other side, so it's going to become a positive 3 volts. It was negative 3 on the left, and I need to switch it over to the right, so it becomes a positive 3 volts there. If I do that with the next equation I have, we'll start with I1s. How many I1s do we have there? Well, that's a 6, that's I3, that's a 6, that's I2, that's an I3. So we've got 0 I1s. So 0 I1s. How many I2s? Well, I've got plus 4 I2. So plus 4 I2s. And then how many I3s? Well, I've got plus 2, plus 2. So that's plus 4 I3s. That has to equal. And I've got minus 6 plus 6 is 0, and then 0 switched to the other side is still 0. Okay? So these are my 3 equations. I'm just going to do something real quick. I'm going to put a 1 in front of the I1 in the first junction equation, a 1 in front of the I2, and a 1 in front of the I3, because technically that's what I had up here. 1, negative 1, 1. Okay? This is the setup for row reduced echelon form. And what we want out of these are actually just the coefficients in front of every variable. I want 1, negative 1, 1, and 0. I want negative 4, 0, and positive 3. I want 0, 4, 4, and 0. With these coefficients, I can set up what's known as a matrix as the following. This matrix, they're going to look a little weird because you're not used to them, but they're going to look like this. They're just going to be the coefficients. It's going to be 1, negative 1, 1, and 0. It's going to be negative 4, -4, 0, and 3. And then we're going to have 0, +4, +4, and 0. And this is what's known as an augmented matrix. So sometimes you'll see a line being put down there like that. Okay? Now, specifically speaking, sometimes you'll see this in your linear algebra courses. Because we looked at I1, I2, and I3 in the columns, sometimes you'll see written above this I1, I2, and I3. You can put that if you like. We kind of know what we're doing here and what we're trying to find. So this is some matrix. And we're just going to call this equal to matrix A. Okay, so this entire thing here, this entire thing is now just variable A. Which kind of seems like a lot, just throw it into one variable, but that's what we want there. On your calculators at this point, you can pretty easily solve this. What you're going to do is you're going to go into a mode you've probably never used before. If you're using a Texas TI 84 Plus Silver Edition with a pink background that I got my junior year in high school from a different student in class, Larry, if you're out there, you know who you are. We're going to go into this matrix mode here. It's 1, 2, 3, the fourth button down on the left hand side. It's the inverse of X, and it's in blue, so you have to hit second. But if you go second matrix, and then you go to the right twice to edit, we're going to edit variable, or the matrix A. So if you click that just on the first one, that's matrix A. It's some variable that we're using here. There's matrix A. Then we can create a 3x4 matrix. Okay, so in the very top when you start off, you're going to have some flashes up there, like right up here in the beginning. I don't know if you'll see that at all. But you're going to switch that to a 3, hit enter, and then by 4 matrix. So whenever you hit enter after entering that 4 in, you should have 3 rows going down, and if you hit to the right, you should have 4 columns going over. Okay? And all we're going to do is we are going to create the matrix we have here on the sheet in our calculators. So in that first row, we're just going to type in 1, -1, 1, 0. In the second row, it's going to be -4, -4, 0, 3. And in the last row, it's going to be 0, 4, 4, 0. Okay? And once we enter in that last value, we can just hit second quit. That's the mode button, but the second function. And then now we're going to go back into the matrix, second matrix, and then we're going to hit right, and we're going to go into the math. Okay? And what we're looking for is we're looking for this row reduced echelon form, RREF. So I'm going to start scrolling down. It starts off with DET, which stands for a determinant, and then number 2 has this little T there, which is a transpose. Then we look at dimensions, and then fill, and identity matrices, and random M, and then augment, and what are all these things that we're doing. But when we get down past 0, and then we see A, that's REF, and then B is RREF, and that's what we want. So whenever we get to that RREF in the math section of the matrix, we can hit enter at that, and it will show us on our screen something that looks like this at this point. It'll just say there RREF parentheses. And then the cursor is just like blinking here, like, what the heck do you want me to do? Well, what we wanted to do is we wanted to apply row reduced echelon form to matrix A. So what we're going to do is we're going to go back into the matrix function. We keep going back to the matrix. So second matrix, and then in the first column there's names. These are the names of the variables. We put a matrix value in to variable named A. So you're just going to select A right there. If you would have put the variable into B, you'd select B. If you put it down into, I don't know, like J, you'd go and select J. But we put ours into A, so let's just select A here. So if you hit enter on A, you should see that this RREF now shows this in your calculator, where this right here, that is the matrix variable. okay? And if you're familiar with computer programming at all, what we're doing here is we have some function, the row reduced echelon form, RREF, and we're passing into that function variable matrix A. It's some array vector, you can think of it that way. And then we're just going to, for sanity's sake, close off the parentheses here. So we have it look like this now. RREF, parenthesis, bracket, A, close bracket, parentheses. And when we slam enter on that, we're gonna get this like really weird looking thing. When we hit enter on that, we're gonna get a screen that pops out, and it's going to show this matrix. It's gonna show it a little bit different on your calculators, but what it's showing is this: 1, 0, 0, 0, 1, 0, 0, 0, 1. And then it has negative 0.5. Oh, here, I'll draw it like this. Then it's got negative 0.5, negative 0.25, and then 0.25. Okay, so what the heck is this actually doing here? What are we looking at? Well, this 3 by 3 right here, this is what's known as an identity matrix. Oftentimes in linear algebra, this identity will just be written as a capital I. And what it represents is that I1, I2, and I3 have been solved for essentially. This identity matrix is just saying, look, if I were to rewrite this top row again, it would look like this. 1 I1 plus 0 I2 plus 0 I3 equals negative 0.5, which means that I2 and I3 don't actually exist. And 1 I1 equals negative 0.5. Well, this just means here that I1 equals negative 0.5 amps. We just solved for I1. What we see here is this negative sign means that we were going the wrong way. Remember, we chose I1, I2, and I3's direction just randomly in the beginning, okay? So we just had it backwards. What this means here is that when we look at this identity matrix, this stands for I1, this stands for I2, and this stands for I3, which means we can just say that I1 is equal to 0.5 amps, I2 is equal to 0.25 amps, and I3 equals 0.25 amps as well. And then since I1 and I2 were negative, what this should have looked like back in our loop is I1 should have actually been going the opposite direction, and I2 should have been going the opposite direction. So I1 should have been going this way, and I2 should have been going this way. And we just didn't know that to pick it. Maybe you had an intuition to pick it because you're like, hey, Coach Bots, if these are 6 volts and 6 volts, maybe they're going to push that 3 volt instead. You know, we've got more potential in the 6s, so we're going to be pushed into the 3. Maybe you made that logical argument in the beginning, but even if you didn't, even if you just chose randomly for the currents and randomly for the Kirchhoff loops, the row-reduced echelon form and how we solve this matrix here will give us the correct answer. Okay, so we're able to get the currents just by doing these 3 Kirchhoff loops, well, 2 loops and then 1 junction rule, and then set it up into a row-reduced echelon form, have your calculator crunch through it, and then boom, all of a sudden you get the right answers. And if you have any negatives there, you just need to flip a direction, and it's no biggie. Okay. One thing that I was always taught, and I've always just followed this rule, I've just always taken it as it is. Notice when we did our loops here, we stayed in the center. We made a closed loop like this, and then we made a closed loop here. I've always been taught that that's the best way to do it. I've been told that if you make a loop going around the outside like this, that actually doesn't help you at all. It doesn't give you any new information. I've never gone back to fully reprove that. It's just what I've been told there. So I've always done interior loops, and I've never had a problem with that. So I would suggest that you always choose interior loops as well. I was told that if you do an exterior loop just on the edges, you actually don't gain the information that you need. But I need to go back and I need to rerun that to make sure that, you know, that professor wasn't just telling me some nonsense. But I believe that professor is very good at what he does. So yeah, that's a Kirchhoff loop. Set up your circuit, you choose your currents, choose your direction of loops, create a junction rule, create 2 loops, and then boom, 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 you're all done. And set up that matrix and let the calculator go to town. Okay, so that's it. That's Monday's lecture. It was a little longer of a video here, but if you're using this, it is an important thing that pops up in circuits. Pops up every once in a while in the AP Physics C E&M test. I believe it did last year in 2019's test, because that's technically this year. So yeah, it does pop up. It is something we see there. What we'll be looking at later on, though, is right now this circuit only had EMF sources, these voltages, these batteries, and resistors. What can we do with Kirchhoff loops if we also can include other components like capacitors, which we've played with a little bit, and inductors, which we have no idea yet what those are. So we'll see that a bit later. But thanks for watching the video. This problem is finished. Take it easy.